All right, hello everyone. My name is Jacob Magnon. I am in Physics 2211, and this is the first lab of the year for constant velocity. Let's get straight into it. So before we get into the lab, we're going to start off by showing some of the formulas and principles that we need to know. Then we're going to analyze the momentum principle, electronically track the data, and then compare that to a computational model, and then finally answer some questions at the end about what happened and why. So in this lab, we want to visually demonstrate the properties of Newton's second law, also known as the momentum principle. We're going to compare experimental data to a computational model of expected motion and see how they differ or if they differ at all. All right, so we're going to look at some of the important formulas that we need to know. The first one being that the final momentum is equal to the initial momentum plus the net force times delta t. So this is pretty much going to tell us that when the net force is equal to 0, the final momentum should be exactly equal to the initial momentum. Then if we divide this entire equation by the mass, we're going to get a very similar formula that says the final velocity equals the initial velocity plus net force over m times delta t. And this is also going to tell us that our velocity is going to stay constant if no force is acting upon it. As far as the process for this experiment, we're going to first record a ball rolling across the floor and then track that video using a software. Then we're going to break down each frame to tell us the ball's actual position and time, and that will be used as our observed position. Then we're going to develop a computer code to match the initial conditions of velocity and position of the test, and then it's going to run a program to predict the motion of the ball. After that, we're going to graphically compare the observed position and predicted position to see if they are different. What we're looking at here is the tracking software as it shows the ball's position at each frame. And then over here, we see a graph of the ball's position versus time. As you can see, it's negative and fairly linear because the ball is moving to the left at a constant velocity. So some of the things that we need to take away from the tracking software are the total time that the ball was rolling and its initial position and velocity. The velocity was calculated using the first and second frames of the video. These are going to be important to construct our computational model to predict the motion of the ball. Alright, so in order to make our model, we're going to first input our initial conditions of velocity and position, which we can see here. Then we're going to adjust our delta t and our position update vector in order to accurately describe what the tracking software saw. So since our frame rate was recorded in 45 FPS, we're going to divide our delta t so that it's 1 over 45. Then our position update vector is going to be negative 0.029 because that is our velocity divided by 45. So what we're looking at here is the observed data compared to the predicted data, which we made using our computational model. As you can see, the observed data actually does not follow in a linear slope like the predicted data does. It actually starts to get farther and farther away from the predicted data as the time intervals grow larger. Now this is because our predicted data does not actually account for forces like air resistance or friction that are happening in the observed data, but are nowhere to be found in the computational model. Some possible errors made in this video are one, the ball not rolling completely straight relative to the camera, some tracking misplacements when we're going through the frame-by-frame selection of center of mass, and then maybe some rounding errors like when I rounded 1 over 45 to 0.022. Now, some questions you may have are, what if the axes were flipped? So if I had flipped the axis 180 degrees so that my ball was rolling in the positive x direction, the graph would have shown a positive slope looking a little bit like this, where it goes like that, instead of like we had going in the negative direction. So what does it mean? This experiment tells us that our predicted motion shows what happens when there's zero net force, And in this case, those forces are the gravitational force and the normal force, which sum up to be 0. What it doesn't account for and why the graphs are different is because there are other forces like friction happening that we don't account for.